right, welcome. Been a while since we've done a video, but I'm back. Let me straighten out this camera here. Speaking of been a while, the camera's a little off kilter. All right, so today we're going to be talking about limits some more. Okay, we just talked about it in class as sort of a review and thinking about number sense. Here we're going to talk about some limits that would be limits that frankly would have been just not possible for us to really be able to tackle if it weren't for a rule. And so the rule is what the title is here, and it's French, misspelled French, if I recall correctly. It is L'Hopital's rule, L'Hopital. And so the real spelling, I think, doesn't have the S, but either the guy was misspelling his name or somebody long ago misspelled his name, and we just like sort of stuck with it because, you know, change is scary, right? Anyways, so L'Hopital's rule is going to be helpful for thinking about limits like the one that's given right here. So what if we have the limit as x approaches 1 of the natural log of x over x minus 1? So a thing that you might do initially to sort of get this started is go like, cool, so let me just plug it in. Natural log of 1 over 1 minus 1. And so to evaluate that numerator, e to what power gets us 1? Well, 0, power of 0. Bottom is also 0, and that doesn't make us sad, it makes us happy. 0 over 0 means that it's a number, it's some number, we got to figure out what number it is. That's where the issues start happening here, because if we think about times when we have confronted 0 over 0, there have been ways to sort of work around it. For example, the first sorts of limits that we tried to tackle were things like the limit as x approaches 1 of x squared minus x over x squared minus 1. Well, this one, if you plug in 1, you'll also get 0 over 0. So this is 0 over 0. And we were happy because it meant, well, we got to do something. And in this case, it was to factor and to divide out the common factor. We won't actually do it. But that's the game plan for this one, is like, oh, I can factor that numerator, I can factor that denominator, and there's a removable discontinuity that I can divide the common factors. Okay, well, if I look over here, that's not factorable. So like we're thinking about like restructuring it. So it's not expandable, it's not factorable. You know, log properties aren't going to be really helpful here because it's just log of x. Like it's not like anything interesting happening with that logarithm. All right, so then you start thinking about, so what's another sort of thing that we could do? Well, we have also confronted the limit as x approaches 0 of sine of x over x. And again, if you plug in 0 there, you get 0 over 0, and that made us happy. Now, this was one that we could factor, though. So how did we do it? Well, we attacked it from a geometric standpoint and looking at the unit circle and creating a series of inequalities and eventually using the squeeze theorem. The natural log doesn't have a very intuitive geometric sort of counterparts to work with. So, you know, for a while, people thought like things like this, well, you know, there's a number, we just can't find it yet. And then along came this Frenchman named L'Hopital who created this rule. Maybe. What we find out often in math is that the person it's named after is not the person who figured it out. So it's possible that this guy, L'Hopital, never actually figured it out. What is his first name? He's in here somewhere. I'm looking at my textbook here. L'Hopital. I don't know. You could do a Google for him. Anyways. Oh, there he is. Marquis de L'Hopital. There you go. So, sorry, I'm reading right now. Oh, it was discovered, this actual rule was discovered by the Swiss mathematician Jean Bernoulli. This is all really important. This will be on the test. I'm kidding. It is not on the test. Anyways, so let's talk about what is the rule. What's L'Hopital's rule actually saying here? So the rule is that if a limit is of the indeterminate forms, indeterminate meaning can't be determined, forms 0 over 0 or infinity over infinity. Remember, that's just sort of the way we write a small number over a small number or a big number over a big number. Those are not always 1 because the small numbers may not be of the same magnitude. The big numbers may not be of the same magnitude. So if we have a limit, okay, and when you think about like plugging in, it's like that's getting turbo small over turbo small, or that's getting turbo big over turbo big, then this rule applies. If that doesn't happen, the rule does not apply. You cannot use L'Hopital's rule whenever, just in these cases here. All right, so if we have a limit of this form, then the limit as x approaches a of f of x over g of x, so it's got to be written as a ratio like this, is equivalent to the limit as x approaches a of f prime of x over g prime of x. So in other words, if you are dealing with something like 0 over 0 and infinity over infinity, and like you can't find a way to factor it or go about it in a different way, you can take the derivative of the top and take the derivative of the bottom and try to evaluate the limit then. Note, we do not use the quotient rule. So even though it's written as a quotient, we are not actually using the quotient rule here. We are literally just taking the derivative of the top and the derivative of the bottom and reevaluating it that way. The reason why this works, there's a pretty clean proof for the 0 over 0 case. Less clean proof for the infinity over infinity case. I'd urge you, go look at, like, there's a video I'm sure you can find for 0 over 0 case. Infinity over infinity is, I've found like sort of like paragraph proofs that are sort of more about intuition that seem to make sense to me, so see if you can find those as well. We're not going to go over the proofs in class. We just want to sort of use these rules. So let's use the rule for the first time here. So let's look at the one we were trying to evaluate at the very beginning of all of this. So what is the limit of natural log of x over x minus 1 as x approaches 1? And so we know that if you just plug in, you get 0 over 0. And so that makes us happy. Yay! So let's see what happens when we do it. So we are going to, I like to put in a little L apostrophe H as I sort of apply the L'Hopital. It's really for like me going back and looking at my work later on. I can more quickly recognize what's happening. Otherwise I'm like, wait, why did I change that thing to that thing? And now it's more obvious, like, oh, I applied L'Hopital in between. So let's do it. L'Hopital. So limit as x approaches 1, that stays the same. The derivative of the natural log is 1 over x. The derivative of the denominator is just 1. So this, of course, is just 1 over x. And now there isn't an issue of substituting in. The substitution gets us 1 over 1, which equals 1. So in this case, 0 over 0 was 1, but not always. All right, let's take a look at the next one. So we have now the limit as x approaches infinity of e to the x over x squared. And so this, when you think about substituting it in, is infinity over infinity. And that is one of the indeterminate cases we can use. Now you might already have an idea of what this is going to be because it's comparing an exponential function to a quadratic. And for many times in your algebra classes and pre-calculus classes, you probably thought about which one's growing faster and whatnot. But we're actually going to prove that it works, that what we think is growing faster is in fact growing faster. So we're going to apply L'Hopital. So the limit as x approaches infinity of derivative of e to the x is just e to the x. The derivative of the denominator, x squared, is 2x. All right. And at this point, you're maybe expecting to come up with some sort of answer here, but let's check it. If you substitute in a very large number, that numerator is still large. That denominator is still large. Granted, smaller than it was before, but still approaching infinity. We have, once again, an infinity over infinity case. And there's nothing in the rule about how you can only use it once. You can use it as long as you have one of these two cases. And since we still have this case, the rule still applies. So now let's apply L'Hopital once more. So we'll have the limit as x approaches infinity of e to the x over 2 is what we get. Well, now let's think about that. Numerator heads towards a big number, and the denominator stays at 2. That means that we can actually evaluate this. The limit here is positive infinity, since we're basically just looking at half of e to the x. And that means it will just continue to grow without bounds as x gets bigger and bigger and bigger. So there you go. You can use it 2 times, 3 times, 4 times, as many times as you want to. There are some where you kind of get stuck in a circle, and that's not fun. But yeah, that we can talk about those if we ever confront those together. All right, last one. Number 3, limit as x approaches pi of sine of x over 1 minus cosine of x. So if we apply L'Hopital's rule, the derivative of sine is cosine. The derivative of cosine is negative sine, so that will be sine of x. And then we sit there and think about, so what if we were to plug this in here? We get that's, what do we get here? We get, well, that approaches -1, and the bottom approaches, oh boy, 0. We got to split this up into 2 things. We got to go left hand versus right hand. Or do we? I totally did not do this problem correctly. I'm going to pause for a moment and see if you can figure out what mistake did I make doing this problem. And then I'll let you know in just a couple of seconds here. All right, why is this all wrong? Well, I didn't do something that I did in the other 2 problems that is always a good idea, which is to check whether this limit meets the conditions of the rule. The conditions is that it must be of the form 0 over 0 or infinity over infinity. And I did that for example 1 and 2. I didn't do it for 3 on purpose because I wanted to sort of point out to you that if you don't check, you could really screw yourself over. Here we go. The limit as x approaches infinity, or in pi. So sine of pi is 0. Cosine of pi is -1. So this is 1 minus -1. So 0 over 2 is the form. That is not indeterminate. That is not 0 over 0 or infinity over infinity. It's also not like, what is that? It's just 0. So this limit can be evaluated just by simply plugging in. So don't get into the assumption that every single limit from now on needs to have the L'Hopital's rule applied to it. Simply not the case. So that's it for today. We'll talk more about this in class and take the survey after this to let me know. Thanks.